Okay, we're continuing on here, chapter 14 to so obviously we got into titrations last time, and we talked about again a couple of different types of titrations. We talked about our strong acid, strong base titration, again yielding us a titration curve that you'll make next week. Looks just like that. pH and volume of base, equivalence point, right about there. And it looks something like this. And as we talked about, really for all the titration sort of curves, there's four different parts to it. There's, again, our initial part, our before the equivalence point, at the equivalence point, and after the equivalence point. So in this type of titration, as we talked about, again, at the very beginning, before you start titration, you pretty much only have a strong acid, which means that essentially will be your H plus concentration. And you could go right into the pH equation to get the pH of your solution. Once you start the titration before the equivalence point here, step number 2 there, you do need to do an ice table. And as we've talked about a number of times at this point, you do need to do it obviously in molds because you're adding volume in this case. And really the purpose of the ice table is to figure out at this point how much of your strong acid you got left over after it reacts with whatever you're adding, sodium hydroxide, for example. That will then leave you at the end of that ice table really just a strong acid left over, which you definitely want to convert back into molarity using the total volume. And then you could go back into the pH formula as you have a strong acid left over. At the equivalence point in this type of titration, as we talked about, we pretty much have only a salt left over because, as we mentioned, sort of your definition of equivalence point is the moles of acid and base are equal to each other. So what that leaves you here is a salt, and again, that salt does come from a strong acid and a strong base, which means the salt will not go through hydrolysis. And we would expect the equivalence point in this type of titration to be around neutral and a pH of 7. As you go past the equivalence point, you are really adding excess amount of base. And in this particular case, you do again need to do an ice table. And the purpose of this ice table is basically to figure out what is the concentration of your strong base that's left over at this point, because obviously you've gone past the equivalence point. You'll convert back to molarity at the end of that ice table. And because, again, that is the concentration of a strong base, that most likely will be your hydroxide concentration, which would allow you to get to the POH and then to the pH. So here, basic ice tables here on steps 2 and 3 to figure out what you have left. Now, we saw a similar sort of titration curve of a weak acid and a strong base. And in both of these cases, the setup is the base is up in the burette and the acid is on the bottom there, what you're adding to. Also going to yield you a titration curve-ish type of thing here. Maybe a little like this still, equivalence point. And we have, again, the same sort of 4 parts to it. The difference, though, is as we were talking about at the very beginning here, the only thing you have to begin with before you start titration is a weak acid, which means because it's a weak acid, it does require really an ice table sort of problem, basically just a Ka type problem like we did at the beginning of this chapter to figure out what X is. You could do that in molarity because you have not added any volume at this point. You could solve for X, that will give you your H plus concentration, and then you could go into your pH. As we start in this type of titration, in the second step here, you're basically doing what you were calculating buffer at this point, and what's going to happen between the reaction that's going to occur. And what you will always end up with at the end of that ice table is the formation of a buffer, pretty much. And you can convert that back into molarity like usual. And then because you should end up with a buffer, it should be an acidic buffer, you could go into the Henderson-Hasselbalch equation to get the pH. You also alternatively could avoid the Henderson-Hasselbalch equation and just do an ice table if you wanted to take that approach. Here at the third part, thank you, of the titration at the equivalence point, once again, We're not going to have any acid or base left over because they should be equal to each other and basically get used up. We will be left with a salt. Now, because that salt, part of that salt does originate from a weak acid, here at the equivalence point, we do expect it to actually go through hydrolysis. And what that means is you really have to do an ice table. The first ice table is really to figure out what is the concentration of the salt you have made. The second ice table that you have to do is a hydrolysis ice table. That salt reacted with water. And in this case, it will form hydroxide. Because it comes from a weak acid, it will act as a base when it reacts with water, which means it will accept the H plus from the water and make OH minus, which will give you the basic pH. So in this type of titration, we do expect a basic pH here at the equivalence point. Normal hydrolysis sort of calculation, things that you want to keep in mind is you most likely, again, will have the wrong K value here. You'll probably have the Ka value when you get into that hydrolysis sort of ice table. You will need the Kb value. So you got to use that Kw equals Ka times Kb, and that will get you your pH. Past the equivalence point here is very similar to the first one. You will end up with basically two things at this point. You will end up with that same salt that will go through hydrolysis, but you also have the presence of your strong base that's left over at this point. And out of the two, the strong base is much stronger than the salt going through hydrolysis. So at this point in the titration curve, or the contribution of the salt, and we just look at the strong base that's left over. And because of that, that gives you your OH minus concentration, and that gets you to POH and then to the pH. Any questions on any of those titration curves there? All right, then two titrations are fun, but three is better, they say, I suppose. So let's take a look at another titration, which is this one. This is going to be a titration of a strong acid with a weak base. So we could take something like hydrochloric acid and react it with ammonia, which is a weak base. The setup on this titration is a little bit different than the other two, and that is up in the burette is the acid, and down in the beaker is the base. So in this case, we're adding acid to base. That's also why when you look at the titration curve here, it looks upside down. And that is because we're actually starting at a higher pH because we're starting with a base. And as we add the acid, our pH is going to start to drop and come down. We still have sort of that S curve just kind of upside down happening. Not probably surprising, just like the other ones, there's the same four spots on this titration curve. We have before we start, again, before the equivalence point, at the equivalence point, and obviously past the equivalence point here. And just like we did on the others, we're going to talk about sort of each of these steps and what's going on at each of these steps. So let's just start with the first one here, which is before we start the titration. Again, the only thing we have basically sitting there is ammonia in this example. And that is a weak base, which means if I want the pH of a weak base, this is basically a Kb type problem. So a little NH3 plus some water. Again here, with the bases, you may want to put the water into the equation. I'll erase my picture here so I don't run into it. And we're going to end up with NH4 plus and OH minus. And again, you actually can keep it together or break it apart, your call, but we'll take it apart. This is just going to be, as obviously the H plus is going that way. Change here, so we're going to go molarity. This is just going to be molarity, and X is this table. This is going to go into our KB. We're going to solve for X. The important thing to remember, once again, though, when you do solve for X, that is the hydroxide concentration, not the H plus concentration. So that's going to get you a POH first and then into a pH. So kind of similar to the previous titration, instead of having a weak acid to begin with, we have a weak base, which again is just a Kb type calculation like we did earlier in the chapter. And again, you could use the molarity because you haven't added any volume at this point. and that'll get you your hydroxide to your POH and to your pH. Obviously, you can do normal things like assumptions or however you want to kind of solve that. Any questions on that there? All right, so let's take a look at second part, which is before the equivalence point here, and see what's going on there. So at part 2 here, we're going to go before the equivalence point. So obviously we're going to get the reaction that we saw there. We got a little HCl plus some ammonia. Going to make some NH4 plus and Cl minus. Once again, if you want, you could combine those two as NH4Cl, your choice, whichever way you want to do it, or you could keep them separated, your call. For the point of this, I'm going to keep them separated, but you can definitely keep them together if you want. So we are adding the HCl in this case, and we are starting with this. So just like we did previously, I'm just going to make up some numbers here. So we're going to start with our 4 moles of NH3. Now, as just like all the other ones, if for the equivalence point, we should less moles of what we're adding than what we started with. And again, I'll just go with 2, which is less moles, NH0. Change going to be -2 here, -2 and +2. And that's going to give us here 0, 2 moles, and 2 moles. At this point, like normal, we'll convert back into molarity using the total volume. And again, at this point, you can hopefully see what you got going on, which is we have made a buffer, right? We have these two things left over. Just like in the other titration, we also made a buffer at this point, which would be NH3 and NH4 plus or NH4Cl as well. I'm not worried about the Cl minus once again, really, because it is a neutral salt, right? Because it comes from a strong acid. So, you don't have to worry about it. So just like in the previous one, you will always hit a buffer here in this type of titration before you reach the equivalence point. The difference between this one and the last one is it'll be more of a basic buffer than an acidic buffer. But because it's still a buffer at this point, to get the pH, you could go into, once again, your Henderson-Hasselbalch equation, or again, you could do a second isotable if you wanted to in this case as well. Any questions on that there? All right, so that brings us, as we can see, when we take a look at our titration curve, we're making a buffer through here, right? And now we're really starting to blow through our buffer. And kind of like what we see with the other ones, in this case, because we're adding acid, we'll actually blow through our buffer. We'll have a pretty good drop to the equivalence point, and we will have a secondary drop after the equivalence point as well. But we will drop down to our equivalence point. And let's see what's happening here at the equivalence point. So at the equivalence point here, we still have our reactions, so our HCl, our ammonia, and our NH4 plus, and our Cl minus in this case. And again, adding this guy, starting with this guy. So again, we're going to do it in moles. So we'll go our 4 moles here. Since again, we're at the equivalence point, we should know for sure the moles of the HCl should be exactly the same, right? That's basically your definition. Again, here you can't choose the wrong number, hopefully, since there's only one number to choose from. Choose that number. And that's going to get you 0, 0, and a 4 moles here back into molarity at this point. Now, again, when we look at it, we're really left with a salt here. And as we just talked about, obviously, we've been ignoring this part of the salt, so we don't have to worry about the chloride. But the NH4 plus we do have to worry about, because the NH4 plus obviously came from our weak base. And because it comes from our weak base, it will go through hydrolysis here. So much like the last one at the equivalence point here, you will again produce a salt that will go through hydrolysis because it comes from a weak base. And because it comes from a weak base, when it reacts with water in the hydrolysis reaction, it will act as an acid, which means, again, it will donate its H plus over. And in this case, we're going to end up with NH3 and H3O plus in this case, right? So without doing a calculation here at the equivalence point, my equivalence point should be acidic, basic, or neutral. Should be acidic here. We're producing H3O plus. And again, that's different than what we saw in the previous one where we're producing hydroxide through hydrolysis, which we expect it to be basic. And that's different than the first one we talked about where we have a neutral salt where the pH should be 7. So sometimes people, when they do titrations, always kind of just lock in on like the 7, like it always should be 7 at the equivalence point. Again, that's only specifically for a strong acid, strong base titration. If you're doing this type of titration, you should expect an acidic equivalence point. And if you're doing the middle one that we talked about last time, you should expect a basic pH. So depending on the type of titration you're doing, your equivalence point may end up at a different sort of location in terms of pH. Now here, we're going to basically take our equivalence point here, equilibrium concentration, and carry that down. And that's going to be our initial concentration here in our second ice table. Got to do some zeros. This is going to be just a normal sort of X type situation. And that's going to give me my molarity minus X, X, and X in this point. Now, at this point, this is going to go into our K expression, and that's going to give us our NH3 or H3O plus and our NH4 plus. By the way, this would be a K what? A K A, yes. So again, most likely we'll have a KB given to you in this problem because of NH3. So once again, that KW sort of conversion is what you're going to need to use here. Good news is, though, when you solve for X in this particular case, as you can see here, it will actually equal the H plus concentration, which means then you can go right into the pH. So very similar to the last titration curve we talked about, you will hit basically a hydrolysis reaction here, and again, should produce H plus and should be acidic because it comes from that weak base. Any questions on that part there? Now, lastly here, we're going to go past the equivalence point because those indicators don't stop you. You just keep going. And in this case, if we go past the equivalence point, we're basically just going to be dumping in a bunch of acid at this point. We go past the equivalence point. Once again, we're going to have our reaction. And again, we are adding this and starting with that, right? So initially here we'll have 4 moles of our ammonia. And now because we are past the equivalence point, we should have more moles of what we're adding than what we started with. Because at the equivalence point, they're equal to each other. So again, just making up the number of 6 in this case, it will go 0. At this point, we do get that switch that we've seen before. In this case, now our NH3 is going to be the limiting reagent and will be what is used up in this case. And that means we end up with 2 moles here, nothing of this, and 4 moles at this point. Just like normal, good practice, convert these things back into molarity using our total volume. Taking a look at what we got left over, is that a buffer? No is the right answer, right? This is not a buffer. HCl and NH4 plus are not related to each other. We basically have 2 things. We don't have to worry about this guy, still neutral. We have basically our salt that's going to act as an acid, and we have HCl, which is definitely a strong acid. So very similar to what we did in the previous titration. At this point, the major contributor is not going to be the salt. It is going to be the strong acid. So we again ignore the contribution from the salt. And this will essentially give us our H plus concentration, which will get us our pH at that point. Questions on that there? Yeah. Yeah, what we're talking about in these last four things here is specifically for a titration of a strong acid with a weak base. And again, in this situation, we're actually adding the acid to the base. Yeah. Other questions? So in this one, again, much like the previous one, there's four different types of problems in here. And again, it's similar to the last one, but because we're dealing with a base, slightly different. So instead of a weak acid like we had in the last one, we have a weak base to open it up. We still both have a buffer before the equivalence point in each of those type of titrations. We also have hydrolysis problems at the equivalence point in each of these ones. One's going to be basic, one's going to be acidic, and we have basically a strong acid at the end in this case, or a strong base in the previous titration. So as I mentioned before, these are all calculations we did previously, obviously, in this chapter. The key for a lot of people is understanding what they should be doing, right? And that's the trouble for a lot of people. So sometimes, like I mentioned earlier, it's a really good idea just to take a moment and think about where you are in the titration curve. Are you at the equivalence point, before the equivalence point, or after the equivalence point? Especially in these last two titrations, because it can really tell you the type of problem you should be doing. So if you're before the equivalence point, you know at some point you should be doing really a buffer type problem. If you're at the equivalence point, you should be doing like a hydrolysis problem. If you're past the equivalence point, you should do a strong acid or strong base problem. So just taking a moment, sort of figure out where you are before you jump into the calculation should hopefully help you with the calculation, because directions are always good, they say, right? Rather than just driving around trying to find the place. Although you might eventually get there. Might take you a lot of paper, right? To run through. Any questions on any of that there? Why don't we try one here? Why don't we just do I don't know. Let's do what is the pH after 23 milliliters of 0.1 molar HCl is added to 25 milliliters of 0.1 molar ammonia. Kb for ammonia, 1.8 times 10 to the minus 5. Go with that. See what happens. All right, so give it a go. All right, let's take a look. So we're gonna definitely do our titration here. So we're gonna do a reaction, and we got our HCl and our NH3, making our NH4 plus and our Cl minus in this case. Once again, we are adding this guy. We're starting with this guy. So we do need some moles here since obviously we're doing titration. So our starting moles there of HCl is 0.023 times 0.1. Going to get us 0.0023 moles. For our NH3, 0.025, converting our milliliters into liters, 0.1. 0.0025 moles, NA0 in this case. First off, am I before? Am I after? Am I at the equivalence point in this case? I am before, because the moles of what I'm adding is less than what I started with. So I'm definitely before, equal at the equivalence point, more moles of what you added after the equivalence point. So I'm before the equivalence point. So that automatically should tell you what type of situation we're going to end up with. So let's see if that is true. Our change is going to be our smaller number, which in this case is our HCl. And we're going to add here. That's going to get us 0 for our HCl, 0.0025 minus 0.0023. Going to get us a 0.0002 moles and a 0.0023 moles here. At this point, we do want to convert back into molarity using our total volume. So we started with 25 milliliters. We added 23 milliliters. Looks like a 48 milliliter situation. So here we want to divide by it in liters. So 0.048 liters for both of them. And that's going to get us here. Looks like 0.00417. And 0.0479 molar. At this point, if you're not sure what's going on here, we don't have any of that to worry about because that's neutral. We have NH4 plus and we do have NH3. And knowing that I'm before the equivalence point in this type of titration, that should remind me that, oh yeah, that's a buffer, right? That should be happening at this point. Since that is a buffer, we could go right into our Henderson-Hasselbalch equation, pKa plus the log of the base over the acid. I do have the Kb given to me, so again, a couple ways you could get it, but if you want the Ka, that would be Kw divided by your Kb. And if you put that in there, our 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, you'll end up with 5.6 times 10 to the minus 10. That's going to give us a pKa equal to minus the log of our 5.6 times 10 to the minus 10. Gives us a 9.25 here. And if we pop that in there, it's going to give us a 9.25 plus the log of my base. Remember that the one with one less hydrogen is the base there. 0.00417 divided by 0.0. Like maybe I lost a zero there. We'll try that again there. Did I lose a zero? Did not. It looks like all right, 0.0479. All right. So doing the math there, looking like dividing, little log action. We're going to add that to a 9.25. It's going to get us a pH here of 8.20 at that point, which I think is pretty good based on this. This is this titration, so that's between those two numbers, so it's pretty good at that point. Alternative to this, you could have rolled with the pKb, subtracted 14, got the pKa. You would get 9.26 for your pKa. No big deal. Pretty close. And also, you could have used the POH version of the Henderson-Hasselbalch equation and then subtracted 14 at the end as well. Any questions on that one there? All right. Well, now comes your turn to work out problem time, right? All right, so we're going to work out these problems here. You're starting with 100 milliliters of nitrous acid, 0.1 molar nitrous acid. You're going to titrate it with 0.1 molar sodium hydroxide. We're looking for the pH at 4 different spots. What is the initial pH? What is it after you've added 80 milliliters of your base? What is the pH once you reach the equivalence point? And what is the pH at 105 milliliters? Now, again, a reminder that when you get questions like this where there's multiple parts, you should think of each part as just like a separate question, like you're always starting at 0 and you're going directly to that point. The volumes don't add from one part to the next usually. Ka value here, 4.5 times 10 to the minus 4. Go after it. I'm going to nap for 30 minutes and then I'll wake up and we will see how you did. Okay, hopefully you made a little bit of a dent into here. Let's go over it and see how we're doing. All right, so we have some different spots here on our titration curve. And first off, you definitely see a Ka value, which means this is a weak acid, and sodium hydroxide is a strong base. So we are doing a weak acid, strong base titration here. Again, like we talked about here, our sodium hydroxide would be adding to our weak acid in this case. All right, so with that being said, we'll start with part A here, which is the initial solution before the titration begins. So basically A here is before we start. So really, before we start, all we have sitting there in our beaker, our flask, is our 0.1 molar nitrous acid with the T. And again, that's a weak acid with a Ka value of 4.5 times 10 to the minus 4. So we will do basically just a weak acid ice table type of problem here. where we have our weak acid that's going to dissociate into H plus and NO2 minus. In this case, since we have not added any base, we can just do this table in molarity. So some zeros. We're going to do some minus x's, plus x, plus x. This means at equilibrium 0.1 minus x, x, and x so far. At this point here, we will go into our Ka expression. And popping that in there, it's going to give us x squared 0.1 minus x is equal to 4.5 times 10 to the minus 4. At this point, we can assume x is equal to 0. And if you did, you will see no good. Yeah, about 6.7%. A good reminder to make sure you always check your assumption. So in this case, the assumption is actually not good. That means we do need to solve this through quadratic here. So that's going to give us x squared, and I'm going to multiply this to the other side, 0.000045 minus 4.5 times 10 to the minus 4x, bringing everybody to the same side, x squared plus 4.5 times 10 to the minus 4x minus 0.123445 equals 0. Going into our quadratic here, that's going to be minus 4.5 times 10 to the minus 4, plus or minus. If you do everything in the square root, I think you get 0.001802. And then if you square root it, I think you get, can't remember in there, 0.01342, I believe. So 001432, I think, is what we get there. That's going to all be divided by 2. So minus 4.5 to the minus 4 plus 0.01342 divided by 2 gets us a x value of 0.006485. Going the subtraction route is not going to be good because that's going to get us a negative number, and that negative number will be negative 0.006935. So obviously we can't have a negative number since h plus equals x. So that means that our x value here will be our H plus concentration, 0.006485. That can then go into our pH. And that should yield us here an opening pH of 2.19 for our titration. Yeah. Any questions on that there? So again, a reminder, assumptions don't always work, so make sure you do check it. All right, so that's part A. So if we're sketching our titration, we're like there, maybe. All right, we're at now B, and we want to know what is the pH after we add 80 milliliters of our base. And in this case, we will get a reaction. So we're going to add 80 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar HNO2, still the same Ka value, 4.5 times 10 to the minus 4. So clearly here we're going to get a reaction. So we'll go a little sodium hydroxide here, plus our HNO2. Going to make some water, I believe, and a little sodium nitrite here. Obviously, we are adding this guy, and we are starting with this guy. So we need to do this table in moles. So 0.08 times 0.1 gives us 0.008 moles of our NaOH. 0.1 times 0.1 gives us 0.01 moles of our NHNO2, and a 0. We are, if you're not sure, right, we are at this point before the equivalence point, since the next part is the equivalence point. But I know that again by looking at the moles that I'm adding to what I'm starting with, I have less. So I am definitely before the equivalence point here. That once again should give you an idea where you should end up with this calculation. So once again, let's see if we do end up in a buffer situation. Yeah, let's see. So we're going to subtract the smaller number. That's going to get rid of our sodium hydroxide. That will leave us here 0.002 and 0.0080. Here we will convert back into molarity. So our total volume at this point in the titration is we had 100 milliliters we started with. We added 80. That's 180 milliliters total. That means we'll divide by 0.18 liters here to convert these guys back into molarity. And if we do that there, go 0.002 divided by 0.18, can give us a 0.0111. Feel like a 444 is coming here. Just see. A 0.0444 molar. At this point, as I mentioned, as you should hopefully know even before you started the calculation, we have HNO2 and NaNO2, which again is a weak acid and the salt of its conjugate base. And once again, as we should expect, we have made a buffer at this point. And because it is a buffer, we can probably easily get the pH by using our Henderson-Hasselbalch equation. We're going to need a pKa value here. So that's going to be minus the log of 4.5 times 10 to the minus 4. That's a 3.35, looks like. So popping that in, 3.35 plus the log of our base, which is this guy. So that is 0.0444 divided by our acid. And that's going to get us here 3.95 here as our pH at this point. Any questions on the ice table or any of those calculations? Makes sense so far, right? We're adding some base, our pH went up. Again, if your pH went down at this point, you are definitely going in the wrong direction. Your titration curve is not going in the right way. I'll pop a dot maybe there. All right, so off to C here, and at C we're looking for what is the pH at the equivalence point. So let's go here. So we're looking for the equivalence point pH. And we're adding obviously 0.1 molar sodium hydroxide to our 100 milliliters of 0.1 molar HNO2. Again, still the same Ka value, 4.5 times 10 to the minus 4. Still obviously have our reaction that's going to occur here. So a little sodium hydroxide, a little HNO2. Going to get us our NaNO2 and our H2O in this case. Once again, we are adding our sodium hydroxide. We're starting with this one. So our initial moles here, 0.1 times 0.1 gives us 0.01 moles. Now, in this particular case, they did not tell you the volume to reach the equivalence point, which we will need to know because we will need to know the volume total. But I do know that because I'm at the equivalence point, right, the number of moles of sodium hydroxide I should have is the exact same number, right? So I know that this is 0.01 moles. Now I do have the molarity, right, of my sodium hydroxide. Since molarity is moles per liter, I know the moles now. I know the molarity. I could solve for the liters, which would be moles divided by molarity. Which again, if we did it in this case, we'll take our moles divided by our molarity, which is 0.1. Will give us 0.1 liters or 100 milliliters, right? We could also have used in this case, since it's a one-to-one relationship, M1 V1 equals M2 V2. and solve for V2, where M1 would have been 0.1 molar for the nitrous acid, and V1 would have been 100 milliliters equals M2, which would be 0.1, and V2 you could solve for, which would be what you're looking for. All right, so we know we need 100 milliliters of the base to go with our 100 milliliters of the acid to get to the equivalence point. And again, that's going to be important a little bit later. So that's going to be 0. Good news, you can't choose, hopefully, the wrong number since there's only one number to choose. That's going to get us here 0, nothing, and this. Here is, again, where figuring out the volume is important. So 100 milliliters of the acid, we calculated 100 milliliters of the base. That is a total volume at this point of 200 milliliters. That's a pretty big burette you're using. We're going to divide by 0.2 liters in this case. And we're going to go 0.01 divided by 0.2 and give us a 0.05 molar at this point. Any questions so far? All right, so again, as we hopefully would expect, what we have left with, again, if you're not sure, you look at your ice table, and we basically have a salt left, right? And whenever we have a salt left, we want to think about, will it go through hydrolysis, and will this go through hydrolysis? This will go through hydrolysis once again because that salt comes from a weak acid, right? And that is what we expect to happen here at the equivalence point in this type of titration is really a hydrolysis problem. So we need to lay up a second ice table, and we want to take the part of the salt that's going to go through hydrolysis, and the sodium is not going to go through hydrolysis because it's group 1. It is the NO2 minus that comes from the weak acid that is going to go through hydrolysis here. And it's going to react with water, and since it comes from a weak acid, it will act as a base with water, since it doesn't have an H to give, by the way. We will donate an H plus over, and we will make HNO2, and we will make hydroxide. Again, as we would anticipate, our pH at the equivalence point in this type of titration should be basic because of this, and we are producing OH minus. Carrying down into our second ice table, we're going to use our initial concentration here. And these guys are going to be zeros. Going to go minus X, plus X, plus X. This is going to be 0.05 minus X, X, and X. This will go into our K expression here. Products over reactants. And this is going to be a KB, right? Because of this. And we do not have a KB value. We have the KA value given to us. So we do need to convert that. So our KW is equal to a KA times a KB. That means our KB will be 1 times 10 to the minus 14, which is KW, divided by our KA, 4.5 times 10 to the minus 4. That's going to get us here. I'll call it 2.2 times 10 to the minus 11. So popping in our numbers here, x squared divided by 0.05 minus x equals 2.2 times 10 to the minus 11. We're going to assume x is equal to 0. That's going to get us x squared 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply first and then square root it and see how we do. So we're going to go that times 0.05, a little square root action. That's an error. Try that again. Square root action, right? Buttons. That's going to give us I'll go over here to the left, an x value of, that's a lot of zeros, 0.0000154. 245, I think. 245. Okay, didn't lose one. We do want to check it, so we'll take that divided by 0.05, times it by 100, and we are good. So the check here is good. So as we come back to our table, we can see that the X does equal the hydroxide concentration. So that will equal our hydroxide. We'll go into our POH here, minus the log of what's above. And we'll go minus the log 0.0000001054. It's going to give us a POH of 5.98, and then subtracting 14, right, to get to our pH. 8.02, which is basic. And again, what we would expect it to be. Go right there so you can see it. 8.02, yeah. Question on that one. So again, this is a hydrolysis problem at the equivalence point, producing that hydroxide, which again is why we do expect it to be basic. Any questions on that one there? All right. So we're kind of moving up definitely to 8. Lastly here, we're going to go 105 milliliters and see what we're looking at. So 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our nitrous acid. That is 0.1 molar as well. So we'll still have our reaction here. And obviously here we are going to go with our moles. So 0.1 times 0.1 for our acid, still 0.01 moles. For our sodium hydroxide, 0.105 times 0.1. Going to give us 0.0105 and a 0. We're starting with this one. We are adding this one. And we should hopefully see that we have more moles of what we're adding than what we're starting with. And that means we are past the equivalence point in this case. That means we see the switch that occurs in the smaller numbers that change. So minus 0.01, minus 0.01, and plus 0.01. That means at equilibrium, nothing going on there. 0.0105 minus 0.01, 0.0005 moles, and 0.01 moles. At this point, total volume, we had 100 of the acid, we added 105 of the base. That's a 205 milliliter total volume. We'll divide by 0.205 liters. And if we do that there, 0.205, 0.002439. And for the other one there, 0.04878. At this point, we have two things left over. We have this one and this one. Is that a buffer? That is not a buffer. They are not related to each other that way. We have, again, two bases, as we would expect. We have our salt that will go through hydrolysis, and we have this guy, which is a strong base. So once again, at this point in the titration, we do ignore the contribution of the salt as a strong base. Pretty much just needs to go for a swim and is going to affect the pH a lot greatly by producing that hydroxide. That means that this number is our hydroxide concentration, which is going to allow us to get to our POH by taking minus the log of it there. And that's going to get us here 2.61. And that's going to give us a pH of 14 minus that. 1139, which definitely is basic. And what we would expect at this point, since at this point you're really just dumping in strong base, right? You've gone past the equivalence point and you're just basically dumping in hydroxide into that solution, which should cause the pH to go up pretty high. Question on that there. And to finish out our curve over there, very badly drawn curve-ish. All right, I missed the point. I was a little off there. All right. Any questions on titration, titration problems, titration professionals? You are, yes? All right. We'll lay it up there for today.